57 years ago, in July 1969, the world stood still, staring agog at grainy, flickering televisions as Buzz Aldrin and Neil Armstrong descended from the Eagle lunar module towards the moon. Looking back, it feels almost like a fever dream of ambition. This was only 66 years after the first airplane took flight, but against all odds, we broke free from Earth's gravity and touched another world.
Tranquility Base here. The Eagle has landed.
This frontier-busting feat was presented as absolutely effortless, a triumph of US might. But was it really all plain sailing? What the 600 million or so TV viewers had no idea about was that this mission nearly failed. Behind the scenes, approximately 400,000 engineers, scientists and experts worked tirelessly around the clock, from incredibly detailed plans years in the making to keep it all on track. The slightest deviation could end not just in human tragedy, but also have huge global political consequences. So how did this scientific army plan for every eventuality and stop disaster in its tracks? I'm Alex McColgan, and you're watching Astrum Extra. Join me today as we uncover the incredible science that made the Apollo 11 mission possible. We'll explore the launch, journey through space, and descent onto the moon, digging into the meticulous maths, maneuvers, and materials that kept the Apollo 11 team alive, that most people don't even know existed. The next time you go out at night, look up, find the moon. Hopefully you can't really miss it. And now imagine going there, traveling more than 384,000 kilometers away from everything and anyone any human being has ever known, and actually landing on the moon. It blows my mind to think about, but nearly 60 years ago, 3 humans did just that. On Wednesday, the 16th of July 1969, an estimated 500,000 people descended on the roads and beaches around Cape Canaveral. They were here to witness the launch of Apollo 11, humanity's first attempt at a manned moon landing. A 110-meter Saturn V rocket shimmered in the distance. The excitement was palpable. But what none of these lawn chair lounging enthusiasts knew was that a problem was about to unfold that could stop the mission before it even got off the launch pad. Just as the crew arrived on site, a leaking hydrogen replenish valve was discovered 60 meters up in the 3rd stage of the Saturn V. Not something you want to see just before you're set to take off. Because liquid hydrogen is kept at a bone-chilling minus 252 degrees Celsius, it constantly boils off into gas as the rocket sits on the pad. So the replenish valve allowed the tank to be constantly topped up, keeping it at 100% capacity. This was vital. Without a completely full tank, the rocket would not be able to complete its translunar injection, the burn that would take the craft out of Earth's orbit and towards the moon. The leak was so severe, it could have caused an explosion. So fuel loading was immediately stopped and the lines were quickly drained. It was only just over 2 years since the tragic Apollo 1 fire where 3 crew members had died, so there was no room for error and certainly no appetite for risk. If the leak remained unaddressed, the mission would be over before it even left the pad. So a brave crew consisting of 3 technicians was dispatched to try and tighten the valve, but with a little more than 2 hours to launch, time was running out. The crew were working on the valve, manually tightening each bolt, even as the astronauts were starting to board the craft just 30 meters above them. But when they still failed to stop the leak, the crew took the extreme measure of pouring water from an eye wash station over the valve, where it froze. While the resulting ice successfully isolated and sealed the leak, it rendered the valve completely inoperable. They needed another way to keep the tanks topped up. Engineers decided to try using the large main fill valve to keep fuel in the tank, something it was never intended for. For the final hours of the countdown, 2 engineers worked to keep the rocket flight ready. One monitored fuel levels, whilst the other turned the fill valve on and off, topping up the tanks to compensate for boil-off.
Oxidizer tanks in the second and third stages now have pressurized.
Meanwhile, Buzz Aldrin, Michael Collins, and Neil Armstrong sat in the command module in eerie silence, preparing themselves for launch. Now sealed off from Earth's atmosphere entirely, they were concerned with a different gas, one that was just as critical to their survival as the integrity of the rocket itself. During the planning stages, it had been decided that the Apollo spacecraft needed to be as light as possible. To make that happen, a decision was taken to fill the astronauts' module with pure oxygen. Normal air is 78% nitrogen, so only taking oxygen meant that they didn't need heavy tanks of nitrogen and allowed for the use of a lower pressure within the craft. Combined, this made for a lighter weight spacecraft. Win-win, right? Well, not really. Oxygen is very flammable, and this was a contributing factor in the Apollo 1 fire I mentioned before. After that fire, the gas makeup NASA used was tweaked to a mix of 60% oxygen, 40% nitrogen to make it less flammable. They also pressurized it at a much higher 16 psi, so if any leaks occurred, the air would flow out and not let the humid Florida air in. Once they were safely in orbit, the composition would then gradually be changed to pure oxygen at a lower pressure of 5 psi. But even this amended launch mix caused problems. As I mentioned, normal air is around 78% nitrogen and 21% oxygen. This mix meant that humans have a significant amount of nitrogen dissolved in our blood. Early testing showed that if astronauts took off like this, when the cabin pressure dropped, the nitrogen formed bubbles in their blood and joints, causing a potentially lethal condition. It was therefore mandatory for all the astronauts to change their internal makeup before they even set foot on a rocket. They did this by breathing pure oxygen for roughly 2 hours beforehand to flush out the nitrogen from their blood, which is why you see them attached to what looks like suitcases as they walk to the rocket. That's the oxygen. Having successfully purged the nitrogen from their veins to survive the launch, the crew was ready to go.
10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.
But this was just the beginning of their journey. Now they actually had to get to the moon. The astronauts started to prepare themselves for trans-lunar injection, the engine burn that would send them out of low Earth orbit towards the mysterious moon. This was a particularly dangerous part of the journey, as it required some exacting maths to ensure the correct trajectory. Get it wrong, and they risked being lost to deep space. And they still had to make it out of the lethal radiation field that blankets the Earth, the Van Allen radiation belts. The Van Allen radiation belts are essentially 2 concentric donuts of radiation held in place by Earth's magnetic field. Normally, they act as a shield, protecting our planet and us on it from the solar wind. But for a spacecraft passing through them, they are a high-energy gauntlet. And in the 1960s, the lethality of these belts was a terrifying unknown. Scientists were so concerned that they even conducted high-altitude nuclear tests, including a mission called Starfish Prime, to see if they could physically blow a hole in the belts to create a safe passage for astronauts. Needless to say, this was less than effective and actually added radiation to the belts. So instead, NASA's trajectory experts found a solution in geometry. A team of so-called human computers, mainly poorly paid women who would go on to become NASA's first computer programmers, they tweaked the maths of the translunar injection to exploit a loophole in the Earth's magnetic architecture. It was much safer to go directly out at the North or South Pole, where there wasn't much radiation, but doing so would have used up too much fuel. The compromise was a slant trajectory. NASA precisely angled and timed the launch and the burn so the spacecraft would bypass the high-density horns of the inner Van Allen belt entirely and head through the weaker fringes of the outer belt. But even after making it through the radiation belts, the navigational problems didn't stop. In fact, the chances of things going wrong only got higher. When people think of Apollo 11 flying to the moon, many imagine its engines were burning the whole time. But to do that would have required too much fuel. It would have made Saturn V so heavy, it wouldn't have made it off the ground. Instead, for most of its trip through space, engineers used physics to coast Apollo 11 to the moon. Well, specifically, where the moon would be in 3 days' time. It followed a figure-of-8 geometry that used the moon's mass as a gravitational anchor and free accelerator. This was called a free return trajectory, a mathematical failsafe to ensure that if the spacecraft's engines failed, the moon's gravity would naturally sling the craft back towards the Earth's Pacific Ocean. Once the Saturn V's third stage had provided the initial shove, the spacecraft became a ballistic projectile. It was essentially falling away from Earth, gradually slowing down until it reached the equigravisphere, the invisible tug-of-war point where the moon's gravity finally becomes stronger than the Earth's. From that point, the moon's gravity took over, accelerating the craft towards its destination for free. But this required terrifying precision. If the craft were too slow, it would fail to reach the moon's hill sphere, the zone where the lunar gravity takes over. Too fast, and they would overshoot the target entirely, hurtling into a permanent solar orbit with no hope of return. To hit the right window, the Saturn V's third stage had to ignite for exactly 5 minutes and 48 seconds. But it wasn't just about time. Velocity was also key. The engine needed to add precisely 3.05 kilometers per second to the rocket's orbital speed. A deviation of just 1 second in burn time could mean the difference between a historic landing and a drift into the cosmic dark. Thankfully, it went exactly as planned, taking the Apollo astronauts from around 28,500 kilometers per hour to more than 39,000 kilometers per hour. But as they hurtled ever closer to the moon, the astronauts needed to decouple from the Saturn V rocket. They were currently encased in one of its top sections, which was far too heavy to make it all the way to the moon. The Apollo spacecraft was not a single, cohesive vessel, but a modular stack composed of 3 distinct sections, all housed within Saturn V's third stage. There was the service module, a windowless powerhouse containing the fuel cells and the primary propulsion, the command module, where the astronauts were for takeoff, and the lunar module, the fragile 2-stage craft designed for the lunar descent. While we often imagine this trio flying as a single unit, in fact, it required a complex piece of in-flight assembly known as transposition, docking, and extraction. During launch, the lunar module was stored beneath the command and service module, tucked safely inside the spacecraft lunar module adapter, essentially a protective garage on the upper neck of the Saturn V's third stage. This was necessary because the lunar module was far too fragile to be directly exposed to the forces needed to climb through Earth's atmosphere. Once trans-lunar injection was complete and the crew were coasting towards the moon, they had to build their new ship. Pyrotechnic bolts fired, jettisoning 4 protective panels and exposing the lunar module. The Command and Service Module, or CSM, then detached. To avoid damaging the delicate lunar module with the massive heat of the main engine, the astronauts used only the small reaction control system thrusters, positioned in the top of the CSM's cone to drift a short distance away. At just 3.5 hours into the mission, with surgical precision, pilot Mike Collins turned the CSM 180 degrees, facing it back towards the spent third stage. He then moved in for a nose-to-nose docking, connecting the lunar module to the top of the CSM, essentially wearing it like a hat for the remainder of the 3-day journey to the moon. Only with this mechanical connection complete could they now begin what NASA termed the trans-lunar coast towards the moon, trusting their navigation to a computer with less processing power than a modern calculator. But how did they know they were on course? With no real landmarks, only an empty vacuum. While Project Gemini, the space program before Apollo, had experimented with basic digital maths to aid navigation, the Apollo program represented a paradigm shift. It was the first time human lives were entrusted to a computer for the entirety of a voyage into space. The Apollo Guidance Computer, or AGC, developed at MIT's Instrumentation Lab, was a marvel of miniaturization. At a time when most computers filled entire rooms, the AGC was roughly the size of a briefcase. It was also the first of its kind to utilize silicon integrated circuits, the ancestors of the chips in your smartphone today. By today's standards, its specs were pretty humble, just 4 kilobytes of erasable RAM and about 72 kilobytes of rope memory software that had literally been woven into the copper wire by hand. To know where it was in the featureless void, the AGC relied on the Inertial Measurement Unit. This was the spacecraft's inner ear, a stabilized platform of 3 gimbal gyroscopes and ultra-sensitive accelerometers that allowed the computer to track every nudge of the thrusters and every shift in orientation, maintaining a fixed reference in space without ever looking out a window. But even the most advanced sensors in the 1960s were prone to drift. Over time, tiny mechanical errors in the gyroscopes would accumulate, causing the computer's internal map to slowly lose its alignment with reality. To fix this, NASA turned to the oldest trick in the navigator's book, the stars. From the cockpit of the command module, Mike Collins used a sextant, just like the 18th century sailors did. He would peer through the optics to find 2 specific guide stars from a catalogue of 37 stored in the computer's memory.
Houston, we'd like you to press on to star 44, over.
Then, he used the sextant to measure the exact angle between these stars and the Earth or Moon's horizon. Finally, he fed this data back into the computer, detailed as a P23 sighting, which allowed it to reset its internal gyroscopes. The crew were now on a straight path to the moon, and you might think this meant things got easier. But in reality, it created a lethal thermal nightmare, one extreme enough to rip their ship apart. In the vacuum of space, there is no atmosphere to circulate heat, which creates a world of thermal extremes. The side of the spacecraft facing the sun can bake in temperatures as high as 121 degrees Celsius, while the side shrouded in shadow plunges to a staggering minus 157 degrees Celsius. Without intervention, these massive temperature gradients would have caused the metal skin of the service module to expand and contract unevenly, potentially warping the structure, freezing fuel lines, or frying the delicate electronics nestled just inches away. So NASA used a maneuver called passive thermal control, more colloquially known to the engineers and astronauts as the barbecue roll. Just like a rotisserie chicken over a fire, the spacecraft was set into a slow, rhythmic spin of exactly 3 revolutions per hour, or roughly 0.3 degrees per second. This constant motion ensured that no single part of the hull was exposed to the sun or the cold of deep space for too long. The internal systems and the astronauts inside remained at a steady room temperature of approximately 21 degrees Celsius. It was a low-tech solution to a high-stakes problem, but whilst the temperature was stable, the astronaut safety was a different story. Because out in space, there's one other big threat: radiation. As I mentioned earlier, Earth is protected by a thick atmosphere and the invisible magnetic donuts of the Van Allen belts. But once the spacecraft leaves these protective shields, it enters a shooting gallery of high-energy particles. High doses of these particles could cause acute radiation sickness, nausea, and disorientation, which would lead to fatal errors during a complex lunar landing, not to mention the risk of developing cancer later in life. Solar particle events caused by solar flares or coronal mass ejections could flood the spacecraft with a sudden, deadly burst of protons. These solar storms are powerful enough to not only irradiate human tissue, but to scramble the delicate silicon of the Apollo guidance computer. Since a lead-lined ship would be too heavy to ever leave the ground, NASA had to rely on intelligence and timing. First, they established the Solar Particle Alert Network. This was a global ring of observatories that monitored the sun 24 hours a day. If a major flare was spotted, a warning would be sent to Houston, giving the astronauts time to take cover in the most shielded part of the command module. Counterintuitively, NASA had actually timed the Apollo program to coincide with the solar maximum, the period in the sun's 11-year cycle where it is most active. While this increased the chance of a solar flare, it also strengthened the heliosphere, a bubble-like region of space around the sun and planets caused by the solar wind. During solar maximum, the sun's intensified solar winds acts like a magnetic umbrella, pushing away much more powerful and harder to block galactic cosmic rays. By accepting the risk of a storm they could monitor, NASA shielded the astronauts from the constant drizzle of deep space radiation. But this constant monitoring required a communication line to be open between the astronauts and Earth the whole time, and that's not easy given the 300,000 kilometer distance and the fact that the world had not yet invented fiber optics, a global satellite network, or the internet. In the vacuum of space, there is absolute silence. So instead, to bridge the nearly 384,633 kilometer gap between Earth and the Moon, every word, every command, and every shot of grainy television footage had to be converted into electromagnetic radio waves. Despite traveling at the speed of light, these signals still faced the difficulty of distance, which created a small lag, a delay of about 1.3 seconds each way, meaning an astronaut had to wait nearly 3 seconds for an answer to any question sent to Houston. To handle the massive amount of data needed to be sent back and forth, NASA developed the Unified S-band or USB system. Operating in the 1.5 to 5.2 GHz range, this was a masterpiece of integration. Rather than having separate radios for voice, video, and spacecraft health data, the USB combined them into a single, high-frequency stream. Managing the stream was the Manned Space Flight Network, coordinated by the Goddard Space Flight Center. Because the Earth is a rotating sphere, NASA couldn't rely on just one antenna. They deployed a global safety net to ensure messages got through. This net consisted of 17 ground stations scattered from Madrid to Canberra, 4 tracking ships positioned in the vast stretches of the Atlantic and Pacific, and a fleet of 8 Apollo range instrumentation aircraft designed to catch signals where ships couldn't reach. And all these signals needed to be able to be received by the spacecraft, which had its own specialized technology. The command module used 4 omnidirectional antennas for close range, but once in deep space it relied on a steerable high-gain antenna, a cluster of 4 31-inch parabolic dishes. The lunar module carried its own 26-inch steerable dish, and for the historic broadcast from the lunar surface, the astronauts even deployed a 10-foot collapsible umbrella antenna to ensure the world could see their first steps. But even with all of this, there was a hole. For roughly 48 minutes of every 2-hour lunar orbit, the craft would pass behind the far side of the moon, and the signal would be lost. In this window, the astronauts were truly alone, cut off from all human contact until they rounded the corner and Earth rose over the horizon. This meant that huge sections of one of the most important moments in the mission occurred in radio silence: the descent. In the decade leading up to the Apollo 11 landing, the lunar surface was a scientific enigma that invited terrifying speculation. Without direct physical samples, NASA's planners had to account for a myriad of potential theories. The most prominent of these was the fairy castle theory, proposed by Cornell astrophysicist Thomas Gold in 1956. He argued that billions of years of micrometeorite bombardment had ground the lunar surface into a fine electrostatic dust. In the moon's vacuum, he said, these grains would cling together in loose, porous structures like fairy castles that would have the structural integrity of a spider web. Gold warned NASA that even though on the moon it would be 2.5 tons thanks to lower gravity, a 15-ton lunar module wouldn't be able to land on this surface. It would sink like a stone into water, burying the astronauts in a miles-deep sea of dust. Other researchers, such as J.D. Burnell, feared a different kind of instability. They theorized that the lunar regolith might be pyrophoric, chemically hungry, and highly reactive. He worried that the moment the hot exhaust touched the pristine lunar soil, it would trigger a violent, explosive chain reaction. Even the craters themselves were a source of dread. Some geologists believed that the lips of the lunar craters were so fragile, the mere weight of a spacecraft would cause a catastrophic collapse, tipping the lunar module and leaving the crew stranded on their sides, unable to launch back to orbit. NASA's engineers couldn't disprove these theories, so they did the only thing they could. They over-engineered for every possible nightmare. The lunar module was designed with a wide, splayed stance. Its 4 landing legs contained honeycomb aluminium structures designed to compress upon impact, absorbing the shock of a hard landing and preventing the craft from tipping. At the end of these legs sat 37-inch circular footpads, large disc-shaped snowshoes designed to spread the LM's weight across the dust, ensuring it stayed on the surface rather than sinking into it. Dangling beneath 3 of these footpads were 68-inch long blue probes. They were the spacecraft's cat whiskers. The moment the probe touched the lunar soil, a lunar contact light would glow blue in the cockpit. This was the signal for the astronauts to shut down the engine immediately, a critical move to prevent the engine pressure from building up against the ground and potentially causing an explosion or blowing out a massive, unstable crater beneath them. If the ground began to give way, or if the quicksand proved real, the astronauts had a panic button. The abort guidance system allowed for multiple abort modes. With a single command, the bottom half of the LM, called the descent stage, would be jettisoned, and the other half, named the ascent stage, would fire, kicking the crew back into the safety of orbit. This ability for the LM to split into two halves was the ultimate failsafe. The ascent stage was an entirely independent spacecraft designed to fly even if the descent stage was tilted, sinking, or physically damaged. Inside the lunar module cabin, the paranoia of the unknown continued. Every inch of the interior was stripped of flammable materials, backed by dual redundant oxygen tanks and extra power reserves, because on the moon there was no such thing as a minor complication. The Apollo 11 team was ready for any eventuality, and at 1:44 p.m. ET on the 20th of July 1969, Neil Armstrong and Buzz Aldrin left Mike Collins in the CSM and began their descent to the lunar surface. But it was far from a smooth ride. 12 minutes. That was the time it took for Apollo 11 to fall from orbit to history, and it was a descent defined by chaos. It began with a positional error. As the LM Eagle emerged from behind the moon, Neil Armstrong realized that they were passing landmarks 3 seconds ahead of schedule. A tiny bit of residual pressure in the docking tunnel had given them an extra shove, meaning they were drifting towards a boulder-strewn crater instead of a flat plane they were initially aiming for. Then, the silence was shattered by the 1202 program alarm. Inside the cramped cabin, a yellow caution light flickered. The primary guidance computer, a machine with less memory than a modern car key, was being overwhelmed by cycle steals. In other words, a faulty radar switch was flooding the processor with useless data, forcing it to reboot mid-descent. And while you are dropping to a completely unknown surface at more than 100 kilometers per hour is possibly the worst time I can think of to have IT issues. Down in mission control, 26-year-old Steve Bales had seconds to decide, abort or land. Trusting the software's ability to prioritize critical tasks, he gave the go. But the drama wasn't over. As Eagle dropped below 150 meters, Armstrong looked out the window and saw a crater filled with jagged rocks. If they landed here, the mission would end in a tip-over or a ruptured hull. With nerves of steel, Armstrong took manual control. He tilted the craft forward, skittering over the boulders, searching for a clear patch of dust. In the background, Buzz Aldrin called out altitudes and descent rates while a new crisis emerged, the fuel light. Because they had hunted for a landing spot for so long, 2 to 3 minutes, the fuel was splashing around, triggering a low-level sensor. Houston called out 60 seconds, then 30 seconds. If they didn't touch down before the clock hit 0, they would have to abort the landing and ignite the ascent engine or crash. Dust kicked up by the engine obscured the ground, robbing Armstrong of his depth perception. He relied on the contact light probes dangling from the landing gear. At 4:17 p.m. ET, the blue light flashed. Armstrong throttled down, and the Eagle settled into the Sea of Tranquility with barely 25 seconds of fuel remaining. The troubleshooting was complete. The impossible had been done.
Houston, Tranquility Base here. The Eagle has landed.
Roger, Tranquility. We copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again. Thanks a lot.
Very smooth touchdown.
Man had landed on the moon. But this wasn't merely a triumph for 3 men. Behind every maneuver and step taken on this journey to the moon was a masterpiece of collective human intelligence spanning countless specialities. The mission was a tapestry woven from a million strokes of genius, solves, fail-safes, checklists, and foresight. The physical manifestation of hundreds of thousands of minds working together to push humanity forward in one great leap. It was proof that when focused on a singular, impossible goal, the quiet expertise of many could carry the few safely to a world unknown. But this isn't the end of the Apollo 11 saga. Join me again soon for part 2, where we continue to uncover the scientific fingerprints that coat this mission. We're stripping back the layers of the most iconic armor in history to reveal the scientific secrets of the lunar spacesuit. We'll dive into the high-stakes orbital ballet required to reunite the astronauts in the silence of the void. And finally, we'll face the ultimate trial by fire, the vital physics of re-entry, where a thin shield was all that stood between the crew and a 3,000-degree inferno. The journey home has only just begun.